Okay, let's wait for a few more minutes and actually for another minute to start. Okay, let's begin. So welcome again to the Spring 2024 edition of Introduction to Deep Learning. The title slide usually just says neural networks because these days when we speak of deep learning, we always associate it with neural networks. But you must keep in mind that the idea of deep learning and deep models is more generic. We're not going to venture into the broader topic for this course, through most of this course. So by now, you folks must all have already seen the logistics post on Pienza. So this is, and watch the lecture 0. We have a logistics lecture that has been put out, which explains all of the logistics of the course, and you must watch it. You should ideally also have visited our course website, which is deeplearning.cs.cmu.edu. All course-related information is on the website, so please go to the website at once and take a look if you have not done so earlier, and familiarize yourself with all of the information on the website. Second, you must be signed into Pienza. So all of the interaction, most of the interaction in the course will be over Pienza, where you post questions, and all of our notifications are also posted to Pienza. So make sure that you're signed on to Pienza and you have access. Also, quizzes and such like, and your grades will be posted on Canvas. So make sure you have access to Canvas. And homeworks will be posted on AutoLab. So make sure that you have access to AutoLab. You must also have seen a note on forming study groups. So, and there are forms that are posted. So please sign up for study groups immediately. Our course is highly collaborative. You are encouraged to work together and in study groups. So your best, so it's kind of important to form study groups, because what we found is that students who work in study groups generally perform better than those who work by themselves, because as a team, you learn more, not just from me and the TAs, but also from each other than you would do on your own. Our course philosophy is that we don't want to leave any student behind. In our ideal world, every last one of you would earn an A. And we put in a lot of effort to try to make this happen. No one gets an easy grade in IDL. You have to work for it. But then at the end of the day, we try to make sure that our course objectives are achieved to the maximum extent possible with every one of the students. And historically, this has kind of worked. More than 2/3 of the students typically get some version of an A. It doesn't mean that the A has been easy, but it does mean that people do get an A. There are lots of course resources. We have 20 TAs who are all working to help you and work with you. We encourage you to work in study groups, and we actually form these groups for you. If you cannot form them on your own, collaboration is encouraged. We have 40 office hours weekly. And then I'm always available. You can always email me or just walk into my office if I'm free. Again, remember that you outnumber me 250 or 300 to 1. So don't expect instant response unless you walk into my office, simply because I have so many of them to deal with. And then, of course, your classmates and friends, all of them are allowed to help you within parameters, which I'll mention briefly. And so use all of these resources. The course is a lot of work, but the semester in general is a lot of work. And if you ever find yourself under stress, unable to perform for whatever reason, please reach out to us, to your TA member, or directly to me. We will do everything in our capacity to help you. Then this Friday, so this week, our first lecture is on Wednesday. Typically, our first lecture is on Monday. So we sort of align our course along weeks to make sure the topics are completed at the end of a week. And that kind of breaks down when we start the course on a Wednesday. So to make up for this, we will actually have a second lecture this week. And I'm going to be using the usual recitation slot, which is on Friday, 8 a.m. to 9:20 p.m. for the second lecture. This is a one-time occurrence. And this second lecture will also be on Zoom. We will resume recitations and labs on the Friday slot from next week on. Also, we have hackathons every Saturday, where for several hours, we have students come in and we help them work through homeworks and quizzes and such like. So we will have a hackathon on Saturday, this Saturday as well. And the hackathon combines as many things. First, it's a meet and greet where you get to meet your classmates and make friends or collaborators and form study groups if you have none. So use that as a resource to actually get familiar with the people you will be working with, because they are your greatest resource. If you already have a study group, come as a group. It helps. Second, in the same hackathon, we are going to have a lab where we will teach you how to get started with deep learning code. And finally, of course, the usual attraction for graduate students, there will be food. We'll have pizza. So come back. Our course objectives are as follows. By the end of the course, you should be able to understand some of the theory behind neural networks. You should be able to build your own neural network components and tools. And you should be able to work on large-scale problems. Let's go through each of these bullets briefly. When we speak of understanding some of the theory behind neural networks, we want you to understand the what, the why, and the how, which is to be familiar with the math and to understand where it comes from. And occasionally, we will also present history to contextualize this. Also, understanding the theory behind neural networks contextualizes how you work with them. So bullets 2 and 3, building your own neural network components or working on large-scale problems, are often best performed when you understand the larger context of the model itself. So understanding the theory helps. And finally, understanding the theory really helps you develop and extend your ideas in the topic beyond what is taught in class. So this will help you in your research and in grad school and in job interviews. You will be building your own neural network components and tools. This is done through homeworks, the part ones of your homeworks, and several of the homeworks also have bonus problems, which also help you build your own neural network components. The idea is that if you find yourself in a toolkit desert, you will be able to, we are training you to build your own stuff from scratch so that you can always be empowered. And knowing how to build things is often far, far more useful than simply knowing how to use pre-existing tools, because that actually gives you a much deeper appreciation and knowledge of the subject. So part ones of your homeworks will be intended for this. Part twos of your homeworks are for the more important problem where you learn how to use neural networks to work on large-scale problems. Your homeworks consist of several problems. We typically use speech recognition and a little bit of computer vision as platforms for your homeworks. Again, I don't want you to think that this is a speech recognition course or a computer vision course. These are just examples that we use because these are very convenient and accessible problems on which you can exercise your skills. But whatever you learn in these homeworks should hopefully generalize beyond these homeworks. And then finally, those of you in 11785 will work on a course project. And those of you in 11685 will be given a fifth homework, which is pretty similar in scope to a course project. And so those of you who are coming up with your own course projects may have projects which relate to any of the above three topics: understanding theory, building toolkits, or working on large-scale problems on some novel ideas or something reasonably cutting edge. My lecture style is verbose. I'm going to use lots of pictures. I avoid the equations if I can. Given a choice between deriving an equation symbolically and explaining it with 30 slides of pictures and animation, I usually prefer to present visualizations. So you're going to see lots of pictures, lots of slides. And if this is not how you like your lectures to be, this class might not work for you. Just warning you in advance. Attendance is mandatory. Some of you are in uncomfortable time zones. Those of you in Silicon Valley for whom it's going to be 5 a.m. right now. And some are stuck in faraway places like China and whatnot. Those students are exempted from in-class attendance. They will be required to watch all the lecture videos which will be posted on the web. There are some students who have conflicting requirements, and these students have received special permission from me. Besides the students who have received permission from me and those who were in bad time zones, everybody else must attend, and you get marks for attendance. We're going to use in-class polls to determine class participation. This will be in the form of multiple polls posted at random times through the class. And the polls are going to be on Zoom, in Zoom lectures, or on Pienza, in-person lectures. You must respond to all polls. We're not scoring you on correctness, only on whether you responded, because we don't expect you to be accurate all the time, but we do expect you to keep following. And more importantly, these polls act as ways of recapitulating everything that has been presented until then in the class. And so that is important. Now, those of you who have permission to watch videos instead of being present in class, the ones in poor time zones with special permission are required to watch the videos on MediaTek. MediaTek, not YouTube, because MediaTek lets us know who has been watching, and we can get these statistics from them, and we'll gather your attendance from them. The class is intended to be interactive. We like you to talk. We like you to ask questions. We like you to engage. And my philosophy through the years is that there's absolutely no question that you can ask in class that is silly, wrong, or embarrassing. If you ask a question which to you seems naive or kind of embarrassing, what this really means is that I have not succeeded in conveying the concept to you properly. So the only embarrassment is mine. It's never yours. If you have a question, do not feel embarrassed or shy to ask. We like you to ask because often it turns out that we get the most intuitive questions and we get the best insights into what is being covered through your questions. Now, I like it, interaction and engagement, so we keep trying different tactics. You might be given pseudonyms, and when your pseudonym is called, you must answer the question. I don't know is an acceptable answer, and sometimes the questions may not even have a proper answer, but this is just my way of making sure that people are following along with what we're talking about. So please participate. This is a dumb classroom. Now over Zoom, I cannot really evaluate whether or determine if you are paying attention or not, but then statistics tell us that about 80% of attendees of meetings and classrooms on Zoom stop paying attention after the first few minutes. with very high probability. About 2/3 of you in class right now have other windows open on your computer and you're looking at them. Some of you are looking at your phones. Don't do that. I mean, you're sort of wasting a class by not paying attention. So for classes, in-person classes, your phones and laptops are required to be shut at all times, except if you have to answer polls or if you can show that you're annotating lecture slides. If we find you using your devices for any other purpose in the classroom, we may, in fact, we will ask you to either turn off your device or leave the room. And last but not least, I'm handicapped. Now, it's kind of embarrassing that I have to tell you this, but I have issues. My back and neck are bent. I look odd. I cannot raise my arms. On some days, I can't walk. My breath runs out midway through the lecture, most lectures. And so as a result, I need help and I have strange mannerisms. And if you find these things to be distracting, I'm sorry, but I cannot avoid it. That's how I'm constructed. So any questions before we continue? Do we have any questions? I'll wait a few more seconds and then I'll continue with the lecture. Okay. So we have 227 people on Zoom right now, which means that there are about 205 students of the 270 odd who are enrolled. So which tells me that even in this first lecture, a good many of you are absent. We will take note, but please try to be present. Also, my slide decks often have many hidden slides that are there in the PPT, but are not shown during the lecture. But these slides will feature in your weekly quizzes. So after class, please go through the slides which are uploaded on the course website and take special note of the hidden slides because these might relate to your quizzes. There will be a quiz this weekend, released on Friday night and due by Sunday midnight. And this quiz might invoke some of the hidden slides. So today's lessons, continuing from here, we're going to go through a brief history of neural networks and connectionism, its relation to cognition and the brain, and how it contrasts to conventional computer architecture. We'll look at some early models and their limitations, and we'll introduce modern neural networks and what they can compute. So unless you have been hiding in a cave, you would know by now that neural networks are pretty much taking over all of AI. And anybody taking this class is clearly aware of this, right? They've been successfully applied to various pattern recognition, prediction, and analysis problems. And in many problems, they have established the state of the art, exceeding previous benchmarks by large margins. And sometimes they solve problems that you simply could not even solve using earlier machine learning methods. Now, neural networks were not all the rage forever. In fact, they have become so popular very recently, although people have been working on neural networks since when? We'll see in a few minutes, right? But for a very, very long time. And that's because of some breakthroughs that were demonstrated in recent times. Now, as it turns out, in the early 2000s or late 1990s, if you wrote a paper on neural networks, most machine learning conferences would probably reject your paper outright because it was not an interesting subject. But then in 2016, this happened. People have been trying to build automatic speech recognition programs since the 1950s, but we didn't quite match human performance even in 2016. So in early 2016, if you had used something like Siri, you'd have found that more often than not, it made some embarrassingly funny errors when it was trying to recognize speech. And then in October 2016, Microsoft published this article for the first time where they claimed that they had their AI, their automatic speech recognition system, had beaten humans at speech recognition on a specific speech recognition task. This was the first time that a computer-based speech recognizer outperformed humans, 2016. In, say, September 2016, if you had used Google Translate, we've been trying to translate, come up with automatic translation systems that can translate from one language to the other for decades. And September 2016, we had systems, several of them, including Google Translate, but they didn't work. So if you used Google Translate to translate something from English to, say, German, and then translated that German back to English, more often than not, the original English and what came back from the reverse translation had nothing in common. And we often try to use these as party jokes just to amuse ourselves. And then in November 2016, something astonishing happened. Suddenly, Google Translate began working, and it began working so well that human experts began using Google Translate to come up with their first translation before fixing it. So what happened? Both in the case of Microsoft's ASR system and in Google Translate, what happened is that we began using neural networks for these tasks. And neural networks just ended up being the latest neural networks of the time, just ended up being outstandingly good. The same thing with a task like image segmentation. Here's a pretty complicated image. It's got lots of objects in it. And a computer program has segmented almost all of the key objects and even tagged them. This was a real picture. I'm not exactly sure where this picture is from. Maybe it's from New York. But the fact is, this is working on a real life input and working extraordinarily well. And prior to 2016, performance like this was not achievable. But this became achievable because of neural networks. So also computer games. Now, for the longest time, it was assumed that the standard for intelligence was computer games that required thinking, like chess. And so the standard for AI was building from the earliest times was to try to build a computer game that could actually beat a human in chess. And this remained the standard till the late 80s, when for the first time, a computer program actually beat a human grandmaster in chess. Does anybody know where that computer program was built? Anyone?
Yeah, at Carnegie Mellon.
At Carnegie Mellon. Indeed so, right? And do you know the name of that program?
Yeah, I think it's Deep Thought.
It was called Deep Thought after this computer and the Hitchhiker's Guide to the Galaxy. And as it turns out, this was somebody's PhD thesis, which actually started off as a fun project, which was developed to test some hardware that was built for speech recognition. Anyway, by the mid-1990s, the computer chess programs were so good that even the world champions could no longer compete with them. But then we came to Go. Go is about 10 raised to 60 times more complicated than chess. And we never actually managed to get build a computer program to beat humans at Go. And we kept assuming that Go was the limit of intelligence till 2016. And then in 2016, for the first time, AlphaGo beat the human Go champion. And after that, it's been all the way up. The latest computer games that play Go can start from absolute zero without even knowing the rules of the game. and within a few hours can build themselves up to a point where no human can beat them. And this is also achieved using neural networks. And there are other successes. And in every case, we sort of track it to this magical year of 2016. That was when this first paper appeared, where a computer was able to automatically generate captions for images. This one is man in black shirt is playing a guitar, which is what it is. Construction worker in orange safety vest is working on a road. Girl in a pink dress is jumping in the air. I mean, these are astonishingly good. And it's kind of amazing to think that these captions were generated by a computer, and these were done for the first time in 2016. Before that, this sort of thing was not even in the realms of possibility. And now, of course, we've come a long way. Something like Stable Diffusion can do art for you. ChatGPT can answer all kinds of questions, generate stories, write limericks. There's no end to it, right? So neural networks have come to a place where from everything from astronomy to healthcare and even predicting stock markets, they are establishing the state of the art. So what are these neural networks? Now, in every case, the neural networks is this magical box that takes in some input and generates some output. For example, if it were performing speech recognition, it takes in a voice signal, generates a transcription. If it's captioning an image, it takes in an image, it generates a caption. Or if it's playing games, it takes in a game state and generates the next move to be played. But what's in these boxes? Now, that's what we're trying here to figure out, right? What is this magical box that performs all of these actions? Now, if you think about this, all of these, playing games, recognizing speech, captioning images, all of these are fundamentally human actions. You don't actually see rocks or other inanimate objects going off and playing chess, or even, animals for that matter, right? So since these are fundamentally human actions, maybe if we want to understand how these can be done, we must go and look at the seat of all human intelligence, which is the human brain. Or even before looking at the human brain, our ability to think. So how many of you have actually seen this statue? Anybody? Or picture of the statue? This is the Thinker by Augustin Rodin. And does anybody know who this statue is supposed to represent? Anyone?
Dante
Must be somebody who
Alighieri.
does art. Pardon me?
Dante Alighieri.
So this one is supposed to represent Dante Alighieri, who wrote the Divine Comedy, was it? Right? So anyway, but continuing with our lecture. Our human ability for intelligence. What are the things humans can do? Humans can learn. We can solve problems. We can recognize patterns. We can create. We can even cogitate. You can just be sitting there with no input at all and pondering and coming up with great new things. Some of the world's greatest ideas have come in the shower where there's absolutely no input besides water falling on your head. So this is this amazing capacity of human beings. That's what our intelligence can do. And so if we want to build artificially intelligent programs, these are the capacities we would like to emulate. But for this, we must ask ourselves, how do humans work? How does all this happen? Now, all of this is basically manifestation of the human capacity for cognition. So the real question we are asking ourselves is, how does human cognition work? But as the problem, as Marvin Minsky stated it so succinctly, if the brain, clearly, human cognition arises from the human brain. And if the brain was simple enough to be understood, we would be too simple to understand it. And so it's a daunting task, but that doesn't stop us from trying, right? And so people have been trying for not hundreds, but thousands of years. We've been wondering about the basis of human cognition and the seat of intelligence for well over 2,000 years. The earliest recorded descriptions of discussions on the topic go back to 400 BC by Plato. And the earliest, and surely they were earlier, and people have been thinking about it even earlier than that, but 400 BC was the first recorded instance we've got. And the earliest model for it was something called associationism. Now, how many of you have seen this picture? Anybody recognize this picture? This one? Anyone? It's called the School of Athens. It's a painting by, I think, Raphael in the Sistine Chapel. And it's one of my favorite paintings, or it was until I actually went to the Sistine Chapel and saw the painting. And then I immediately got distressed by the fact that, so this painting shows all of the most famous scientists in the world that were known to Raphael at that time, as of maybe the 16th century. So in the center, you got Aristotle and Plato, you have Socrates, you have all sorts of people, and pretty much all of them in this painting. And I got distressed by the fact that Aristotle's shin is disproportionate in length. And so ever since, I haven't been quite able to appreciate this painting as much as I did before. But anyway, so the earliest model that was described by Plato is associationism. And this is the theory that humans learn through associations. And this theory lasted for over 2,000 years, till 1900 AD, with all kinds of famous scientists like David Hume and even Ivan Pavlov building up entire theories around associationism. So what is associationism, or what are these associations that association actually claims, associationism claims are the basis of intelligence? Associations are literally temporal or physical associations between phenomena. So, for example, lightning is generally followed by thunder. So, you always observe that anytime there's a lightning, there's a thunder immediately opposite, immediately following. You form an association between lightning and thunder. And then, any time later, after having formed this association, if you observe a bolt of lightning, you expect you're going to hear thunder. Conversely, if you hear thunder, then your assumption is that lightning must have struck somewhere nearby. So you form this association. That's what these associations are. And we form associations between all kinds of phenomena. And the fact of the matter is that associationism at some level is still the basis of all machine learning. We are making relationships, associations between percepts, where one percept immediately evokes the other in our mind. But then the question is, where are these associations stored and how? It's all very fine that associations are the basis of intelligence, but where are they stored? Okay, so for this, we have to go back to the brain. By the mid-1800s, scientists had figured out, thanks to improvements in microscopy, that the brain is a mass of interconnected cells, which were later named the neurons. So if you look at the brain closely, the brain has a very large number of neurons, and each neuron connects out to many neurons, and each neuron has incoming connections from several neurons. So the brain is a network of neurons. Now, this was known, and the first person to see the relationship between this connected nature of the brain and intelligence was this guy, Alexander Bain. He was a philosopher, a psychologist, a mathematician, a magician, a linguist, a professor back in the 1800s and early 1900s. pretty much all scientists were polymaths. They were good at many different things, and so was Alex Bain. And in 1873, he wrote this book called Mind and Body, in which he hypothesized that the information that is stored in the brain is stored in the connections between neurons. So all of that stuff about associations, where are they stored? He said they are stored in the connections between neurons. And so here are some ideas he came up with. He not only came up with this hypothesis, I'll get to that later on. He also even drew some diagrams, some circuit-like pictures, which explained how this works. His idea was that the same network of neurons is able to generate different responses, to different inputs, that if you change the inputs, they evoke different responses. Now, this is something that's very obvious to us, but in the 1870s, this was not obvious. And so he said, depending on how the neurons are connected to one another, different combinations of inputs can result in different outputs. Here's one of his examples. Here, each neuron responds if it gets 2 inputs, and you have 3 inputs and 3 outputs, and you see that if you think everything is Boolean, everything takes value 1 or 0. If alpha A and B fire, meaning if they take the value 1, then X fires. If A and C fire, Z fires. But if B and C fire, Y fires. So depending on what inputs you get different outputs, all from the same network. And he even showed that you can build, that these things can be connected so that different intensities of input can result in different outputs. Here, for example, X gets 2 delayed copies of the input. Y gets 3 copies. So if the input is faint, Y will fire, but X will not. But if the input is strong, both will fire. So he actually came up with basically what looks like a modern neural network, where the network produces outputs but for different inputs. So the earliest artificial neural network, believe it or not, dates back to 1873. That's how old this theory is. And Alex Bain even proposed a learning mechanism. He said, when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transmission. Basically, he gave us a model for how the neurons learn to perform their operations and to learn their connections. And his model predicted Hebbian learning, which was actually formalized by Donald Hebb almost 75 years after Alex Bain. Now, so if the first neural networks were proposed in 1873, why did it take till 2016 for things to really, really take off? Now, one of the main reasons was this, that, as Bertrand Russell says, the fundamental cause of the trouble is that in the modern world, the stupid are cocksure while the intelligent are full of doubt. Now, Bain had many, many detractors. People said this doesn't make sense. And in 1873, Bain postulated that you need 1 million neurons with 5 billion connections to acquire 200,000 percepts, these associations. By 1883, 10 years later, he thought harder about it. And he said, well, that doesn't explain everything, because while we are forming associations, in the process, there are many partially formed associations that must be built up. And so we're going to need neurons for those as well. And 20 years later, by 1903, he just said, I apologize, I'm sorry, I was wrong, all of this is nonsense. The brain would need too many neurons for my ideas to work. The tragedy was he was correct in 1873 and he was wrong in 1903. It turns out that the information in the brain is stored in the connections. The brain is what is called a connectionist machine. A connectionist machine is one where You have lots of simple units connected to one another, and the manner in which the machine works depends on these connections. So in the brain, neurons connect to other neurons, and the processing and the capacity of the brain is a function of these connections. So connectionist machines emulate these modern connectionist machines like neural networks emulate this structure. So here's what a connectionist machine is. It's a network of processing elements, and all world knowledge is stored in the connections between elements. Now, connectionist machines are different from your modern computer processors. What is the architecture that modern computer processors use? Can anyone tell me? Okay, Claude, yes, I missed that. It turns out that the human brain actually has about 80 billion neurons. The number is going to vary between people, but it's the order of 80 billion neurons, and it's got 100 trillion connections. There's more than enough capacity for everything that Alex Bain suggested, and more, which is why he was right. I should have mentioned that, my apologies. Anyway, what is the architecture of modern processors? Does anyone know? It's a von Neumann architecture. How does that work?
Von Neumann basically separate the processor from the memory. I learned from the science fiction.
Exactly. The von Neumann machine or the Princeton machine, they separate the processor from the memory. There are different kinds of architectures. In some, you have different memories for programs and data. In others, the same memory is used for both program and data. Modern computers are a combination of von Neumann and Princeton architectures, where in the main memory, outside the processor, programs and data store the same memory, but inside the processor, they use different inside the body of the processor, they use different memory locations. But the point is, the processing unit is separated from the memory. So you can use the same computer to perform different things simply by putting different programs and data in this memory, which is why your simple smartphone can do so many different things, because all you have to do is to change the program in memory. In a connectionist machine, we don't have this distinction. In a connectionist machine, the network, the machine is the program, because the machine has lots of little units connected to one another, and the manner in which they are connected is the program. If you want to change the program, you have to change the connections, which is why we don't actually build real connectionist machines more often than not. We emulate these connectionist machines on von Neumann architectures. And so for a quick recap, neural network-based AI has taken over most AI tasks. Neural networks originally began as computational models of the brain, or more generally as models of cognition. The earliest model of cognition was associationism, and the more recent model is connectionists. Neurons connect to neurons, and the workings of the brain are encoded in these connections. Current neural networks are connectionist machines. So let me release the first poll. Can my TS release a poll? Can you guys see the poll?
Yes.
Which is, sorry, this is the wrong poll. Let me clear this. I'm sorry, it's the wrong poll. I have to back. Yeah. Okay. Can you see the polls? Yep. So the poll is on Zoom. You can actually see this on Zoom. All right. I'm going to stop it for 5 more seconds, guys. And that's okay. I mean, well, most of you got the first question right, and the second question, only half of you got it right. So here was the question. Who was the first person to propose connectionism? What was the answer here for the first question, guys?
It's Alexander Bain.
Alex Bain. And for the second one, how many connections exist?
100 trillion.
100 trillion.
So yeah, there are 80 billion neurons, but there are 100 trillion connections, right? So those are the answers. Anyway, so moving on. Connectionist machines are networks of very simple processing elements, but all world knowledge is stored in the connections between the elements. But what are these individual elements? For this, we're going to go back to the brain. Now, the individual elements in the brain are neurons. Here's what a neuron looks like. It has this head called a soma. It lots of incoming little fibers called dendrites. And signals come in to the neuron through these dendrites. Now, a rough approximation to how the neuron works is that if the total signal coming in through all of these dendrites exceeds some kind of a threshold, then the neuron generates an output, which goes down this long axon out to other neurons. So this is the output. And the axon is the most important part of the neuron. It's protected by this thing called the myelin sheath, which is made of fat. And so an interesting fact is that how smart you are is actually a function of how much fat you have in your head. People have studied Einstein's brain, which is stored. And they found that his brain doesn't have more neurons than the rest of us, but it has a lot more fat. So in fact, it turns out that if someone calls you a fathead, they're actually giving you a compliment. Now, another thing is that neurons don't actually undergo cell division, because if they did, then all of the connections would break and then the information is lost. So you can only get new neurons, but an existing neuron will never divide. So we're going to need a model for this. And the first persons to come up with a model for how neurons operate are these guys, McCullough and Pitts. McCullough was a professor in the University of Chicago, and Pitts was a hobo who just came and knocked on McCullough's door one day, and the two began working together. So can anybody guess which of these two is Pitts? Who's the prof and who's the hobo? Anybody? Someone want to take a guess?
Right.
The prof
One is
is
the hobo.
You're absolutely correct, right? And McCullough was really young when he came in. He was like barely 19. And these two guys came together and wrote this lovely paper called A Mathematical Model of the Neuron in 1943. The actual title is A Logical Calculus of the Ideas Immanent in Nervous Activity. I've read this paper a dozen times and I still don't understand it. But then here's the summary. They actually said that neurons can be modeled as performing Boolean logic. And this was revolutionary at the time. Here's their model of the neuron. They said a neuron has two kinds of inputs: excitatory synapses, signals coming in through this excitatory synapse excite the neuron and make it generate outputs, and inhibitory synapses, signals coming in through anytime you have a signal coming in through an inhibitory synapse, regardless of the other inputs, the neuron will not fire. And they showed that this neuron can actually perform different Boolean operations. So here, for example, in each case, the neuron will fire if it gets 2 or more inputs. So if neuron 1 fires, then a little later, neuron 2 gets 2 inputs and it fires. So this is just a simple delay. Here, what is this Boolean gate? Can anyone tell me? One to the top right. What is this? Neuron 3 will fire if it gets 2 or more inputs. So what is this? That's an OR. What about the one to the bottom left? That's an AND, right? And this is 1 and not 2. 1 must fire and 2 must not fire because 2 is a an inhibitory neuron. So you can perform all kinds of Boolean operations. They even showed that you can come up with more complex things that look like what happens in human perception. So a very common thing that we know is that if you touch a very cold object very briefly, the sensation is that of heat. But if you keep your finger on it for longer, then it becomes the sensation of cold. And they came up with a circuit for it. Here, for example, if you have a very brief cold receptor, then this guy, 1 second later, 1 time instant later, it gets 1 input from 2. But then it gets 1 time instant later, this guy comes in. And this one's response only comes in 2 time instants later because there are 2 legs. So at no time does this actually receive 2 inputs. If you have a very brief cold stimulus, the cold sensor does not fire. On the other hand, if you have a very brief cold stimulus, after 1 time instant, this fires. After 2 time instants, this fires. After 2 time instants, there's nothing coming from here. So this inhibitory line isn't working. And then so after 2 time instants, this fires, and after 3 time instants, this fires. So if you have a very brief cold stimulus, what fires is your heat sensor, but not the cold sensor. On the other hand, if you have an extended cold stimulus, after 1 time instant, you get a signal down this, but after 2 time instants also, because the sensation is extended, you get a signal down this line and the delayed signal down this line, and you sense cold. But then when you have an extended cold input, after 1 time instant, this guy goes up this inhibitory line and inhibits this red neuron. And so it doesn't provide any input to the heat sensor. And so you have a model where a brief cold input makes you feel heat, whereas an extended cold input makes you sense cold. They actually came up with these beautiful models. 1943, right? But then they claimed a little more than they should. They claimed that the networks can compute a small class of functions. They said if a tape is provided, they can compute a richer class of functions and can be equivalent to Turing machines. They claimed they're Turing complete. All of these are true, but they didn't prove any results of this kind, and they didn't provide a learning mechanism. Yes, both of them are, you have different nerves which are going to respond to heat and cold on your skin. So how exactly do these networks learn? We know how it, we have some idea of how this might work. For that, we had to wait for this guy, Donald Hebb, 1949. Now, Donald Hebb was also one of those polymaths who started off trying to be a novelist, became a farmer, then became a hobo, then he became a school teacher, then gave up on all of these and became a psychologist and did some seminal work. So he wrote a book called Organization of Behavior in 1949, where he said when an axon of cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth processes or metabolic change takes place in one or both cells, such that A's efficiency as one of these cells firing B is increased. It's very complicated, but the gist of it is that neurons that fire together wire together. Let me explain. Here's what a typical synaptic connection looks like. The 2 neurons, this incoming signal from neuron A does, in this case neuron X, doesn't actually connect to neuron Y. Instead, there's a little head with all kinds of chemicals on it for neuron X, and when X fires, chemicals are released from here and they excite neuron Y. Now, whenever a chemicals released from here cause neuron Y to be excited. Now, neuron Y is also receiving inputs from other neurons, right? So whenever any signal coming from here causes this to be excited, then this head becomes a little larger, and so this connection gets strengthened. So if I were to write a mathematical model for the weight of the connection between neuron X and Y, you say the weight XY at any time is weight XY plus eta times XY, meaning every time both X and Y fire, then the weight increases by a small value, eta. If one fires and the other doesn't, then this value remains 0, but if both fire, it gets a little stronger. And this simple model as formula is actually the basis of most of machine learning. But what can be a problem with this model? Anybody? What can be a problem? Anyone?
There's no boundary.
There's no bounds. It keeps growing, right? Strong connections will keep enforcing themselves, but there's no notion of competition. There's no reduction in weights. So all of the strengths weights will keep increasing, and eventually all the weights are going to be large. It's going to be it's not really going to have learned anything. It's an unstable rule. People came up with all kinds of modifications for it to try to make it more stable. But then for the real model that worked, we had to wait for somebody else. But before that, let me release poll 2. Right. Can you guys see poll 2? Yeah. Okay, 5 seconds, guys. All right, let me end the poll. So can you tell me the answer? What is the answer?
The second one.
Second one, right? Option B, everything is just going to blow up. If you wait long enough, it's going to be, all the weights are going to be so large that all the neurons are firing all the time. So this doesn't work.
Professor, can I ask a question?
Yeah.
Is there such thing as activation function or normalization in human neurons?
So human neurons actually work slightly differently. So the strength of the connections can decrease. There is the equivalent of an activation function indeed. And the guy who came up with the model for it was this guy, Frank Rosenblatt, who invented this model called the Perceptron in 1958, right? So this was Rosenblatt's original model of the perceptron, which said, he was modeling the human eye. He said the retina had many sensors. These sensors would cause some neurons in something called a projection area to fire. These would cause neurons in an association area to fire. They would cause responses, and these responses would feed back to the association area. It's a complicated model, but then I can simplify it to this model where sensory units sort of feed into associative units, and associative units feed into response units. And how does each of these units work? Each of these units looks like this. Each unit has a collection of inputs, and associated with each input is a weight. So if the weighted sum of all the neurons exceeds a threshold, then the neuron fires. So to answer your question, the neuron gets a weighted sum of inputs. The activation function is a threshold activation. And then if the total input exceeds a threshold, the neuron fires, otherwise it doesn't. So I can write it in math like so. I can say the weighted sum of the inputs minus a threshold is positive, the neuron fires, otherwise it doesn't. It's threshold logic. Is this model making sense to you guys? Is it yes or no? Give me a just raise your hands if this makes sense to you. Yeah. Okay, perfect. I got some yeses. So the problem was that although Rosenblatt's model was fairly complicated, people sort of began associating this with Rosenblatt's model. And the model got hyped, super hyped. They assumed that this model could represent any Boolean circuit and perform any logic. So the New York Times said embryo of an electronic computer. This research was funded by the Navy, that the Navy expects to be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Frankenstein monster designed by the Navy that thinks. All of this was being said about this poor unit over here, and it wasn't true. And because of that, research in neural networks died down because of the overhype. But Rosenblatt was right. He not only gave us this basic model, he also gave us a learning algorithm. His learning algorithm looks a lot like the Hebbian rule, except that in the Hebbian rule, the weight increases if both the input and output fire. Here he said that the neuron has a desired out response, and the weight changes only when the actual response of the neuron does not match the desired response of the neuron. And if the actual response of the neuron exceeds the desired response of the neuron, then the weight will decrease. If the actual response is lesser than the desired response, then the weight will increase, right? Along with the polarity effect. So, and he showed that this is a, what you desire as in what you want the response to be. For example, so this is like training, right? That's and he showed that this rule actually converges for linearly separable classes. And you can indeed see that his basic unit can perform all kinds of Boolean operations. Here's a little, here are 3 instances of this threshold gate. The threshold value is shown inside the circle. The weights are shown inside on the edges. Here, if both X and Y fire, then the total input is 2, which matches the threshold, and so it will fire. So what is this gate? Top left? What is it? Anybody? It's an AND.
And gate.
What about the one at the bottom? And this guy to the right, what is that?
Not.
Not good.
That's a NOT, right? So you can show that this basic unit can mimic any Boolean gate. Unfortunately, it cannot mimic an XOR. And in fact, there is no combination of weights which will make it mimic the XOR. So what we find is that a single, now Rosenblatt called this model the perceptron, but by and by, the individual units of his model ended up being called the perceptron. And we find that a single perceptron, which is like a neuron, is not enough. You need connected, networked elements. This is something that Rosenblatt himself had found. But then just give me a second, I'll be back. So you need to actually connect these elements. And we can see how this works for the XOR. If I have 3 of these elements connected in this manner, then it gives us an XOR. So this now, here, the 3 elements are connected in this manner. The actual output is seen by this guy. So this is your output. There are intermediate elements whose values you're not actually interested in. So we call them the hidden neurons. But this first neuron computes X or Y. The second neuron computes not X or not Y. And this ANDs the 2, and the result is going to give you an XOR. So by connecting up these simple neurons, you can compute an XOR, or indeed an arbitrarily complicated Boolean function. So here is a network of perceptrons which computes this very ugly function. And so this is a multi-layer perceptron where you're connecting up the perceptrons in layers, and they can compose arbitrary Boolean functions. In cognitive terms, they can compute arbitrary Boolean functions over sensory input. And so the story so far is that neural networks, which began as computational models of the brain, are connectionist machines. They comprise networks of neural units. The McCullough and Pitts model neurons as Boolean threshold gates and models the brain as performing propositional logic. This was their invention, the key insight. The brain performs propositional logic, but they didn't give us learning rules. Hebb gave us a learning rule. Neurons that fire together, wire together, but this was unstable. Rosenblatt's perceptron was a variant of the McCullough and Pitts neuron with a provably convergent learning rule, but the individual units in it are limited in their capacity. But by connecting them up in layers, we can model arbitrarily complex Boolean functions. Propositional logic is simple Boolean logic from our perspective. So that. Right. So everybody with me so far? Any questions? Any questions? No. Okay. So let me continue. But is our brain really Boolean? Do we operate on Boolean inputs? Yes or no? What do you think? No, right? We don't operate on Boolean inputs. We have real inputs, right? And we make non-Boolean inferences and predictions. So how does this model work in that setting? For that, let's go back and look at the perceptron itself. Except that instead of having these inputs be Boolean, I'm going to say these Booleans are real valued. The weights have always been real valued. As before, if the weighted sum of inputs exceeds a threshold, the neuron fires, otherwise it doesn't. So what is the shape of the boundary where everything on one side of the boundary all inputs on one side of the boundary causes the neuron to fire, and everything on the other side does not fire? Can you tell me? What's the shape of that boundary? Anybody? So let me give you a hint. The boundary is where the weighted sum of the inputs exactly matches the threshold, correct? That's going to be a hyperplane. Summation wi xi equals t. What is the equation for the what is that an equation for? Summation wi xi equals t. That's the boundary, correct? And so the boundary where, so the network is actually, I can rewrite it like so. It has a function, in this case a threshold function, which operates on a weighted sum of inputs plus a bias term over here. And so this is an affine function of the inputs. Do you know the difference between affine and linear, guys? What's the difference between affine and linear? Anyone?
An affine
The
function
offset,
is
right? Go ahead.
I was going to say a linear function is an affine function that passes through the origin.
Exactly. The linear function is an affine function that passes through the origin, right? And so the neuron has an activation function theta, which operates on an affine function of inputs, where the activation function is 1 if the argument is positive and 0 otherwise. And the boundary is where this affine term is exactly equal to 0, right? So that bound, now I can, once I state it like so, I can change this threshold function to other things, like a step, like a sigmoid or other functions. We'll get to that later. But then staying with our function, the model of the perceptron, what this means is that there's a hyperplane where on one side of the hyperplane, the output is 1, and the other side, the output is 0. So for two-dimensional inputs, if I were to plot the function, that function is going to look like a step. There's a boundary. On one side, the output is 1. On the other side, the output is 0. Everybody with me so far? Is making sense? Yes, no? Okay. I'm just seeing one yes. Maybe I've got to figure out. There's a single hand raised. Okay, thank you. All right. And so once you see that, you can see how it performs Boolean functions, right? For a Boolean operations, for a Boolean functions, the input is either 1 or 0. So if I have 2 inputs, these 4 blue dots are the only 4 combinations possible. Any perceptron that fires on the right side of this line over here, what Boolean function is this perceptron modeling? The one to the left. Or what about the one to the right?
Or
The one to the right is an and this is a not, right? And now you can see why you cannot compute an XOR using a single perceptron. So again, for those who are asking what does affine mean, we'll get to that in the next class again. Okay, I've run out of time over here. I'll let you figure out why we cannot compose an XOR, but then I'll show you how you can use this simple perceptron to compose complicated functions. Let's say I want a decision function of this kind, where I want the output to be 1 inside the pentagon and 0 outside. How can I compose it? I can use one perceptron, which models this boundary. The output is 0 below the line and 1 in the yellow region above the line. The second perceptron models this boundary. The output is 0 to the right and 1 to the left. The third perceptron models this boundary. The fourth perceptron models this boundary. And the fifth perceptron models this boundary. So given these 5 perceptrons, how can I complete this model so that it outputs a 1 only inside the pentagon and 0 elsewhere? Anybody?
And
The only region within which all 5 perceptrons output a 1 is inside the pentagon, right? And voila, I have built a network which captures this pentagonal decision boundary. Now, that's a simple one, but then what if I want to do this? I want the output to be 1 if the input is inside either of these pentagons and 0 outside. How do I do that? I create one subnet for the first pentagon, a second subnet for the second pentagon, then I OR the two, and I get this double pentagon decision boundary, right? And now I can build even crazier decision boundaries. How would I build a decision boundary of this kind? Anyone? How would I do it?
Use a lot of affine functions, and then
A lot of
them.
Not affine functions, right? What I can do is to decompose it into many little polygons of this kind, correct? And then just combine the lot. And so you can compose very complex decision boundaries. Did this make sense? How I can compose even this decision boundary? Give me a thumbs up if you got it. I'd like to see at least 50 of those. All right, yes. All right, I think I got 50. Thank you. And so when I want to have complicated classification functions, it's all about finding decision boundaries. For example, if I want to recognize the digit 2 in images, in the MNIST database, images are 784 pixel data, which means they live in a 784 dimensional space. Within the 784 dimensional space is some region within which all the 2's lie. And so I want to just build a neural network that captures this decision boundary. And we know that if you give me any region of this kind, I can always compose an MLP that captures it. And so what we get is that MLPs can classify real value inputs. They are what we call universal classifiers. For any decision boundary, you can construct an MLP that captures it with arbitrary precision. And so the story so far is MLPs are connectionist computational models. Individual perceptrons are the computational equivalents of neurons. They can model, and the MLP is a layered composition of many perceptrons. MLPs can model any Boolean function because individual perceptrons can act as Boolean gates, and networks of perceptrons are Boolean functions. So MLPs are universal Boolean functions. What we mean by this is that you give me a Boolean function, I can compose an MLP for it. So MLPs can model any decision boundary. Individual perceptrons capture linear boundaries, so I can compose arbitrary decision boundaries by combining these linear boundaries. So they can be used to classify data. MLPs are universal classifiers. Again, what this means is that you give me a classification problem, I can compose an MLP for it. So here is the next code. Okay, 10 seconds, guys. Okay. All right. What is the answer? 7, 6 for each of the lines, and the 7th to and the lot, correct? And most of you got it. Beautiful. The answer is 7. But then we are speaking, so far we've spoken of networks which have, first we spoke of Boolean functions where the inputs were Boolean and the output was Boolean. Then we spoke of functions which took continuous valued inputs but then gave you Boolean or even categorical outputs. But what about continuous valued outputs? In real valued, in most functions, the outputs, in the real world, you also want the outputs to be continuous value, right? How can neural networks do that? For that, let me explain through this very simple figure. Here's a simple 3-unit MLP. It has only, this is on a function of a single input, just a single scalar input x. This first neuron up here fires, meaning the output becomes 1 anytime the input x exceeds threshold t1. The second neuron over here fires, meaning the output becomes 1 anytime the input exceeds the threshold t2. Their outputs are summed with values 1 and -1 respectively. So now, as x goes from a large negative value to a large positive value, what happens is that, assuming without loss of generality that t1 is less than t2, as you keep increasing x, eventually it will cross t1. At that point, it has not yet crossed t2. So this becomes 1, but this is 0, right? And so the output is here becomes 1, and the output here also becomes 1. So the output of the circuit goes to 1. But then as you continue to increase x, eventually it crosses t2. And then t2 also becomes 1, and the outputs of these two neurons will cancel out. And the output of the overall circuit goes back to 0. So this circuit will output a 1 when the input lies between t1 and t2 and 0 elsewhere. Is this making sense, guys? No, that's the weight. Those are the weights of the connections. Vector. Right? Okay. Vector, did that answer your question? Yeah. Okay. And now, suppose you give me an arbitrary function like this blue curve. Here's what I can do. I can partition this input space into lots of little buckets, like so. I can have one little subnet for each of these ranges. And then I can scale their outputs by the height of the function, average height of the function within that range. And voila, I have this network which is going to approximate this blue curve. Then I can make the approximation arbitrarily precise by making these bins arbitrarily narrow. And so an MLP with many units can model an arbitrary function over an input with arbitrary precision. Is this making sense? You guys get this one? How this works? Yes, no, guys? Yeah. Right. And okay. Is it going to be precise? Is it going to be 100% accurate? No, right? But you can make it arbitrarily precise. You give me a bound of error, and I can, oh my God, I just gave away this fourth pole. So let me just ask you this pole, right? How many neurons will be required by a network of sinusoidal activation neurons to precisely model y equals cos 2x? Anybody? It's just going to be 1, right? Because okay, I'll end this poll early because we're running out of time, but the answer is 1. Because, cos 2x is sine of 2 times x plus pi over 2, right? And so to continue with our story so far, we found that MLPs can also model continuous value functions, adding to everything we've seen so far. And so MLPs can do all kinds of other things too. This one, Nimish. So here, if the activation function is y equals sine of z, but I want y equals cos of 2x, then how can I get cos of 2x from sine of z? Right, so that's going to be like saying x with a weight of 2 plus a bias of pi over 2, correct? So remember, went way back when and said that we can have this activation function could be anything instead of a threshold. If I give you a sine, then you can compose more complex functions very simply. That was the point of this book.
Oh, okay, okay. All right, thank you.
So MLPs can also model memory by having loops. They can represent probability distributions, and I'll skip this funny joke, which is not quite funny anymore. It turns out that there are competitions for rubbing your stomach and patting your head at the same time. And usually the guy who wins it is an Indian, don't ask me why. Anyway, so going back to our original problem, the neural network is a function. A function takes an input and generates an output. So given an input, it computes the function layer-wise to predict the output, or more generally, given one or more inputs, it predicts one or more outputs. And in our problem, all of these guys, these are all functions. They take an input and generate an output, right? And so because they are functions, they can be modeled by neural networks, because as we saw, neural networks can model pretty much every type of function. They're not going to be 100% accurate, but they can be approximated to arbitrary error. And so interesting AI tasks are functions that can be modeled by the network, right? And so we've sort of quickly ticked off the 3 questions, that the topics that we said we would address: a history of neural networks, and we've introduced model neural networks and what they can compute. In the next class on Friday, we'll talk more about neural networks as universal approximators and the issue of depth in networks. The class is over, but I'll wait here for questions for a few minutes. Any questions? Any questions, folks?
Hi, Professor. Can I ask about like a previous slide about the MLP modeling continuous outputs?
Okay, which one? This one?
Slide 104.
Yeah.
The one after this. Oh yeah, this one. Yeah. So like in the diagram, like how I didn't understand how like T1 and T2 would produce a square pulse. Like, and I guess like in the previous slide,
Okay,
it said
so
that.
here. So look, when x is greater than T1, what is the output of the upper neuron?
X is greater than T1. Output's
It's 1,
like
correct?
1, yeah.
But what about the lower neuron?
0.
0. So what is the output of this neuron?
1.
If I have a threshold 1, right? But if both of them fire, what is the output here?
0.
Exactly. That's why you get this pulse, right? Or just put a
so
plus over here. That's got it. And so now I can compose this guy. Right?
with different pulses.
Yeah, I can just say